Hello and welcome to today's webinar entitled Real-World Applications of Harmonic Mitigation, Review of Case Studies. My name is Martin Pietrzak. It's my pleasure to be your moderator today. We have an amazing turnout today with over 120 registrants from 28 countries, spanning from North America to as far as Australia and New Zealand. Thank you very much for attending. We'd really like you to hear from you and to include your voice in the conversation. So please ask questions and share your comments. Use the question and answer panel or the chat panel on the right side of the GoToWebinar player to share at any time during the presentation. We will attempt to answer as many questions as possible at the end of this session. Also, feel free to submit any questions after the event via the email at mirrors@mirrorsinternational.com or join the conversation at the Mirrors LinkedIn page. At this point, I want to introduce our speaker, Tony Huvenars. Tony is the President and CEO of Mirrors International, a company specializing in the treatment of power system harmonics. Prior to joining Mirrors in 1996, Tony was Chief Facilities Electrical Engineer at IBM in Toronto. Other work experience includes being a key team member in the computerization of a large oil refinery with responsibility for power distribution, instrumentation, and communication systems. Tony is a registered professional engineer and a member of the IEEE. Over the years, he has gained valuable experience in the resolution of power quality related problems, especially in the area of harmonic mitigation. Tony has published and presented numerous technical papers on power quality and harmonics. Today, Tony will outline some of the real-world challenges that arise from harmonic distortion and the creative applications Mirrors has used to fix them. Using case studies from across a variety of industries, Tony will explore the challenges faced by real clients and reveal the substantial results of their solutions. Tony, welcome, and over to you.
Thank you very much, Martin, and good day, everyone. It's my pleasure to share with you today many of our experiences in applications of harmonic mitigation. Harmonics are a serious worldwide power quality issue, and Mirrors has been assisting customers with treatment for harmonic problems since our inception in 1991. Today we'll be discussing many different real-world applications where treatment of harmonics by passive electromagnetic means were very successful. We'll look at how the harmonic limits defined by IEEE Standard 519 were met in two different applications. We'll highlight an example where harmonic treatment through active means led to serious side effects due to the very high frequency harmonics it introduced. We'll see how harmonic resonance created extremely high levels of voltage distortion in an oil field, and what was done to address this condition, and how passive harmonic filters were applied to comply with IEEE 519 standard. We'll demonstrate how sensitive electronic loads can be protected on drilling rigs and other environments where extreme voltage distortion levels exist. We'll learn how one ship, a cable-laying vessel, saved valuable deck space and significant cost after eliminating the need for rental generators by filtering harmonics to meet marine certifying body harmonic limits. We'll explain how passive electromagnetic devices can be used to eliminate harmonics in broadcasting facilities and film studios. And finally, show how we resolved very high neutral circulating current that was created when generators of dissimilar pitches were paralleled. Our first case study involves a skydiving simulator located in Montreal, Canada. I can say through personal experience that these simulators are a lot of fun. Large fans supplied by variable speed drives produce wind that results in the experience of skydiving. However, the harmonics drawn by the variable speed drives would exceed the limits required by IEEE Standard 519, so the local utility insisted that harmonic mitigation be applied. The consultant considered various options and used Mirrors' free computer simulation software, known as Solve, to identify the best solution. Both reduction in harmonics and energy savings were considered. First consideration was the use of AC line reactors, since they were the simplest and lowest cost option. So what we show here is two of the variable speed drives combined, two 350 horsepower variable speed drives combined for a 700 horsepower load, and a second set of two 350 horsepower VFDs combined for a 700 horsepower load. We ran the simulation, and we can see that there were very high levels of voltage distortion and current distortion generated by the variable speed drives. When we look at the IEEE 519 compliance report that our computer simulation software will generate, we can see that the voltage distortion was well above 5%, and the maximum individual current or voltage harmonic was the fifth, and that exceeded the maximum level of 3. So we failed on voltage distortion. We also failed on current distortion in total demand distortion, and also with individual harmonics. And by applying MIRIS's passive harmonic filters, known as the lineator AUHF, the computer simulations show that IEEE standard 519 limits can be met. The application was simple in that 2 lineator filters were used to each supply 2 of the 350 horsepower VFDs. So again, we have a 700 horsepower total load and a lineator filter ahead of the 6-pulse VFD. We now see that current distortion dropped to 4.1%, voltage distortion went down to 2.9. Our IEEE 519 compliance report shows that we passed both in voltage distortion and in current distortion. In other applications since this Montreal project, similar skydiving simulators, we've used single lineator filters to supply all 4 fans. In other applications of these skydiving simulators, we've applied lineator filters, a single lineator filter on all 4 of the drives, so a larger one that supplies all 4 of the drives, and that has been effective as well. An 18-pulse solution was also considered, and although it could meet the requirements of IEEE standard 519, provided the applied voltage is fairly balanced, because if you have unbalanced voltages, multi-pulse systems do not perform very well. But if the voltage was reasonably balanced, it could meet IEEE 519 compliance. The simulation software was used also to compare the 18-pulse option with the lineator AUHF option to show that significant energy savings could be realized with the lineator solution. This location in Montreal, Quebec, the cost of energy was only 6 cents a kilowatt hour. The facility would run 10 hours a day, 365 days a year. They only took Christmas Day off. And the average load was about 80% load while they were flying. So when we ran that model in our Solve software, we have a comparison report that is generated within Solve. And if we look at the comparison report, we see the reduction in energy consumption and in energy cost. 47,000 kilowatt hours per year, less energy, for a savings of 2,840. So this computer simulation actually is very conservative on the energy savings. This shows a 1% energy saving. As you'll see in the next slides, the actual energy savings realized can be much more significant. At another site in Orlando, Florida, demonstration was done to further highlight the energy savings potential of the passive filter. At this site, an 18-pulse drive was initially adopted. And by switching between the 18-pulse and the 6-pulse VFD with our lineator filter, we could compare the energy consumption of the 2 solutions. With the 18-pulse shown here, running at 60 hertz, fan speed of 889 RPM, the single 250 horsepower fan was drawing 190 kilowatts. When they slowed the fan speed down to 818 RPMs, which required a VFD speed of almost 56 hertz, the power dropped to 152 kilowatts. When we switched to the 6-pulse with lineator, running at full speed, 891 RPMs or 60 hertz, the energy consumption was only 183. So you can see the reduction between the two solutions. And even further reduction was 55, when we ran at 55 hertz, we still got 818 RPM of fan speed. So this is a fan speed that was required. The 55 hertz, we could get to it with the linear filter in the drive at a lower speed on the drive, which reduced the energy consumption even further. So we had 143 kilowatts. So in this case, when we were running at 60 hertz, the net savings was 3.5%, and when we're running at 55 or 60 or 56 hertz to get the 818 RPM fan speed, the energy savings was 6%. So it's much more substantial reduction. In a Bombardier airspace facility near Toronto, a 1,300 horsepower chiller was equipped with a variable speed drive to reduce energy consumption. In an attempt to prevent the negative effects of harmonics, a 5% impedance reactor was included with the installation. However, this added impedance in combination with the already high impedance of the step-down transformer, which was 8% impedance, resulted in a voltage drop that prevented the chiller from reaching its raised capacity. Computer simulation was used to demonstrate why the 5% reactor was not an effective solution. We can see the current distortion and voltage distortion at the distribution panel and at the transformer, not meeting IEEE 519, resulting in distortion of the voltage, flat topping of the voltage waveform, which was restricting the chiller's operation. By replacing the 5% reactor with a linear AHF passive filter, harmonic distortion in the form of flat topping could be reduced and allowed the chiller to reach its full capacity. So we see now the reduction in current distortion, dropping the voltage distortion. Our waveforms now, the voltage peak is restored, current is near sinusoidal. See the current spectrum here, the scale is only 4%, maximum scale here, so you can see there's a little bit of 5th and 7th, 11th and residual harmonics, but it's substantially lower than it was before. And this allowed the chiller to operate without problems. Before I provide further examples of how effective passive harmonic mitigation can be, I wanted to share with you an experience I had with a parallel active filter installation. Prior to joining Mirus in 1996, I was the chief electrical power engineer at an IBM facility in Toronto. IBM has since sold this operation, but the managers in the facilities department there still occasionally call on me to provide consulting services. A couple of years ago, they were having what they believed to be a power quality issue, but were unable to determine the exact cause. The facility was now manufacturing solar panels and solar inverters, and a DC power supply in a photovoltaic tester was failing as soon as it was turned on. These failures began to occur after they installed a 450 amp parallel active harmonic filter, but they were not aware of this when they contacted me. So the slides are on this slide. On the right-hand side, it shows a schematic and the operation of a typical active filter, where you'll monitor the current that's being drawn by the nonlinear loads, and then the active filter through its IGBT network will inject currents that will provide the harmonics that the load requires. Therefore, the power system only needs to supply the sinusoidal component, or the fundamental component. So, in an ideal operation, the active filter can be quite effective in reducing harmonics. When I went to the site and took measurements with a power quality analyzer, I discovered a high frequency ripple on the voltage waveform. Although the overall voltage distortion was extremely low, you can see there's little distortion here with just a real high frequency ripple. the total harmonic distortion was less than 1%, well within any harmonic requirements. The level of distortion near the 41st, 39th to 43rd, however, was troublesome. You can see this is the current being drawn by the power supply at no loads. It's very high frequency. That's shown in the spectrum as being predominantly 39 and 43rd harmonics. The spike at the harmonic spectrum at this level seemed to indicate a resonance condition. So we informed the active filter manufacturer of this problem, and attempts by them to try to improve the LCL filter, which is the filter that's to address these high-frequency harmonics due to the switching of the IGBTs, didn't work. So they tried several attempts at it, improved it a little bit, but it just allowed the power supply to last maybe a couple of minutes longer. Still would fail as soon as it was powered up. The only final solution was to turn off the active filter. So they ended up having no form of treatment on the rectifier and in their inverter test lab. A couple of years ago, we were called upon to provide a solution for extremely high levels of current and voltage distortion at an oil field in Montana, which was equipped with 50,000 horsepower of electrical submersible pumps, or ESPs. These pumps are used when an oil field no longer has the pressure to drive the oil to the surface on its own. All models of ESPs use VFDs and therefore introduce harmonic distortion. At this site, voltage distortion was as high as 19% at the various water stations. So these were the water stations, ESP pumping water stations, where the electrical distribution was, and we can see we've got almost 19% at this Cantor water station in voltage distortion. At one of the utility substations supplying the oil field, voltage distortion was over 14%. This was well above IEEE Standard 519 requirements and was causing problems with neighboring customers. So the utility enforced the standard's harmonic limits on the oil company. Although there were a lot of VFDs at the site, the voltage distortion level still seemed excessive to me. And when the voltage waveform was observed, the oscillations at the peak again seemed to indicate power system resonance. Upon investigation, I found that the utility had previously installed power factor correction capacitors, unaware that the low power factor was due to the reactive power of the harmonic currents and not inductive loads. After significant effort, we eventually convinced the utility to switch off the PFC cap banks, and the results are shown in this table. So we can see when we have both cap banks on, voltage distortion was around 14%, current distortion in the 30% range. We switched off one of the cap banks, the voltage distortion dropped a couple of percentage, and the current distortion dropped significantly. When we turned off all the cap banks, voltage distortion was lowered to less than 9%, and current distortion was also lowered significantly. So we eliminated the resonance by turning off the power factor correction capacitors. I did an earlier webinar on how harmonics have led to 6 power factor misconceptions, which can be found on our website for those interested in investigating this condition further. But I wanted to discuss harmonics and power factor briefly here as well. Harmonic distortion has changed the power relationship from a triangle to a cube. In addition to the inductive and capacitive components, there is a harmonic component, H, that is 90 degrees out of phase with Q and 90 degrees out of phase with the real power, P, in kilowatts. The combination of all 3 vectors is the apparent power S that must be provided. For harmonic generating nonlinear loads such as VFDs, the Q component is usually very small, but the H component can be quite large. And it's that component that lowers the power factor. So improving power factor can only be achieved by mitigating the harmonics. Application of PFC capacitors will often make the problem worse. Even after eliminating the resonance condition, harmonic levels exceeded the requirements of IEEE Standard 519, so harmonic mitigation was required. Various methods were considered, including phase shifting to produce a quasi-12 pulse or 18-pulse scheme, active front-end drives, parallel active harmonic filter, and the linear wide spectrum passive harmonic filter. The active solutions were ruled out due to their high cost and concerns for the high frequency IGBT harmonics that they introduced. The multi-pulse solution was ruled out due to the very poor performance that they achieve in real-world conditions when voltage distortion or voltage imbalance is high. This was evident in the fact that some of the ESPs were already equipped with 18 or 24 pulse VFDs. Their performance was so poor that they did not improve the overall distortion levels. The two charts on the side of this slide show 18 pulse VFD's performance with background voltage distortion, going from no voltage distortion all the way up to 5% voltage distortion. And we show the VFD's performance at full load and at 50% load. And we can see how the current distortion increases dramatically as we increase the voltage distortion applied to the drives. Even worse is what happens when there's imbalance in the power system. This shows that same 18 pulse transformer with perfectly balanced voltages, and you can see the reduction in current distortion is very good. Performance is excellent. But as soon as we introduce 1% imbalance, you can see the THD increases. 2% imbalance, pretty well leaves the chart, and the performance is no better than a 6-pulse VFD without harmonic treatment. Computer simulations were done to show how the existing 6-pulse drives were the cause of the high current and voltage distortion. So we show a couple of 6-pulse drives here running at 85% load. The current distortion is 37%, voltage distortion at 9.8%. Here we can see the simulation's waveform, voltage waveform, spectrum of the harmonics of the voltage with 9.8% voltage distortion, so this is still even less than the actual voltage distortion at the site. And here's our input current, typical double humps, and the harmonic, typical harmonics, so the 5th and 7th, typical of a 6-pulse variable speed drive. And then we ran the simulation with passive harmonic filters applied ahead of the drives. Now we got current distortion down to 6.8%, and the voltage distortion dropped down to 2.6. You can see our voltage looks much more sinusoidal, and current as well. There's residual harmonics. You can see there's a scale at 6%, so there's a bit of 7th, 11th residual harmonics, but overall much improved performance. So the wide spectrum filters were applied to numerous variable speed drives at the site, and with the voltage distortion before, you can see the levels at the 2 utility substations, and after we were comfortably below 5% voltage distortion and 8% current distortion, which was the requirements due to the short circuit ratio as per IEEE 519. For those interested, we have an IEEE peer-reviewed technical paper describing this application, which can be found on our website. We've done many successful projects for the oil and gas industry, including the application of lineator filters on all the drilling equipment for land and offshore oil rigs. But when harmonics are ignored, these facilities can have voltage distortion levels that exceed 20%, resulting in numerous operational problems and equipment failures. In these instances, we have successfully applied lineator harmonic filters as protection for the sensitive electronic equipment. This example shows a land-based rig in northern Alberta where the high levels of voltage distortion were causing the AC drives on centrifuge equipment to fail very quickly. All equipment failures ceased after application of the filter. You still can see that there's distortion on the waveform, and this is due to the thyristor bridges on a lot of the drilling equipment. And as they commutate, if there's a phase-back angle, they'll introduce voltage notch, and that notch can be quite severe when there's no treatment. We can see the notch is substantially lower. It's about half the depth as it was without the treatment, and that was enough to eliminate all of the failures. Again, for those interested, we have an IEEE peer-reviewed technical paper describing this application, which can be found on our website. The next case study I'd like to share with you is an application where a marine certifying body harmonic limits needed to be met on a cable-laying vessel known as the Ocean Challenger. All marine certifying bodies have mandatory harmonic limits because of harmonic problems that are widespread on ships. This is because much of the load can be nonlinear and the power sources are relatively weak generator systems, leading to high levels of voltage distortion. This table shows just some examples of some of the certifying bodies and the requirements of harmonic limits. Most of them are targeting the voltage distortion, total harmonic voltage distortion, and individual harmonic voltage distortions. The cable-laying vessel used a remote-operated vehicle, or an ROV, as shown here, to dig the trench and lay the cables. This ROV was equipped with 10 30-kilowatt thrusters and 4 300-kilowatt electric pumps. They were all equipped with VFDs. Harmonics they generated distorted the voltage well above the 5% limit required by the certifying body, DNV, when supplied from the vessel's main generator. Therefore, 2 separate generators were required to feed the port and starboard sides of the ROVs separately. Owners of the vessel wished to eliminate the rental costs and recover the deck space. So these 2 white boxes shown here are the 2 generators that had to be employed on the ship. Application of 2 750 kilowatt passive harmonic filters, one for the port side VFDs and the other for the starboard side VFDs, reduced the current distortion levels to around 6% and voltage distortion levels below 3 when fed from the main generator. This allowed the ROV to be fed from the ship's main generator, eliminating the need for the 2 additional generators, freeing up that valuable deck space and saving significant rental costs. Facilities with high concentrations of phase-to-neutral nonlinear loads, such as broadcasting studios, can be subject to problems related to third harmonics. At one such facility, the transformer was running extremely hot, despite being lightly loaded, and video noise was ruining the transmission quality. In addition, measurements showed that current harmonics, neutral current, neutral to ground voltage, and ground currents were all high, while power factor was low. So here we can see the ground current at one of the power panels, power panel 5, 7.5 amps ground current, almost 100 amps of neutral current at this panel, very high current distortion, high neutral to ground voltages. Up at the transformer, You can see the neutral current coming from all the panels into the transformer, 120 amps. Ground currents 4.1, a little less than it was at the panel, but still much higher than they wanted. Very low power factor due to the harmonic content. We applied low zero sequence passive electromagnetic harmonic filters at 3 distribution panels at the site. Mears invented these devices in the early 90s, and they have been very effectively used in many applications over the years. These devices provide an alternate low zero sequence path for the triplet harmonics to flow, while phase shifting to cancel 5th and 7th harmonics. So we use 2 parallel connected zero sequence filters and 1 series connected, which introduces the 30-degree phase shift to provide the cancellation of 5th and 7th. Current distortion was reduced by 73%, voltage distortion reduced throughout the facility. Neutral current was reduced upstream of the power panels by as much as 76%, resulting in a reduction in neutral to ground voltage at all power panels. You can see here this power panel went from 3.3 down to 1.3. Ground current dropped from 7.5 to 1.4. And the neutral current dropped from nearly 100 down to 5.4. The drop in ground currents was dramatically reduced due to the reduction in third harmonic distortion. What was happening was the third harmonic distortion was pushing current through the input filters on all of the power electronic equipment through to the ground and creating the ground currents. And that was also was causing the video noise. So the video noise was noticeably reduced with the applications of the HMT devices. Transformer ran much cooler, and with improved power factor, system capacity was freed up. At the headquarters of a large broadcasting facility in Toronto, computer room power panels equipped with the electromagnetic devices were installed throughout, as well as linear passive harmonic filters for the computer room air conditioners and harmonic mitigating transformers throughout the office area. Recently, we discovered another application for our products in the film industry. A new sound stage built by New England Studios near Boston discovered that their electrical distribution system would not be able to handle the high levels of neutral current from nonlinear lighting and dimming systems. They faced a $250,000 upgrade of their wiring to increase neutral opacity, and were being significantly limited on their transformer capacity. One type of lighting used excessively is their KinoFlow. It's very nonlinear, and as it states in its literature. You can see here, as I blow this up, it says KinoFlow ballasts are generally not power factor corrected. They will draw double the current on the neutral from what is being drawn on the 2 hot legs. When one phase, so to demonstrate this, with one phase on, we measured the current in the neutral, and we see that there's a fundamental component. There's a very significant amount of third harmonic, almost as much third as there is fundamental, nearly as much 5th, 7th, and 9th. So very, very high levels of all the odd order harmonics. When load is placed on the second phase, the fundamental and the 5th and 7th harmonics begin to cancel, but the triplets, the 3rd and 9th, increase. With load on all 3 phases, the fundamental 5th and 7th harmonics are almost non-existent, but the 3rd and 9th are very high. And overall RMS current is greater than the phase currents. So here we've got an RMS current of almost 16 amps, and the phase currents are 9 amps each. Switching the loads while measuring the waveforms shows how the pulse phase currents add in the neutral to produce predominantly third harmonic current. So here we have the very sharp pulsed current being drawn by the lighting, the nonlinear lighting. When we add a second load on the second phase, we can see the second pulse added there. When the third pulse gets added, we now have essentially third harmonic current on a 60 hertz system. It's 180 hertz. So here where we have one cycle, in the period that we have one cycle here, we end up with 1, 2, 3 cycles on the neutral or third harmonic. We modified our existing harmonic mitigating transformer technology, the zero sequence filters and phase shifting transformers, to include dual outputs, industry standard cam connectors, and lifting frame to provide portability and ease of application. The HMT removed third harmonic current while phase shifting to cancel fifth and seventh harmonics. Neutral current without the HMT was 154 amps, and with was only 4.4 amps. Improvement in voltage distortion was also very evident. The facility now has state-of-the-art electrical distribution lighting, allowing it to handle these high-tech special effects productions. The HMT auto transformers were installed in the dimming rooms and at the 400 amp company switches up on the catwalks where they drop the lighting systems. And this approach saved the facility nearly $200,000 on installed cost. The final case study to share with you today is an application where two generators of different pitch configurations were paralleled with very high levels of 180 hertz circulating current, resulting in the neutral. So you can see here the two generators. There's our shared neutral. They had 160 amps of neutral current at 180 hertz circulating through the system. A very unique neutral blocking reactor, referred to as GenLink DP&L, was installed in the neutral between the two generators and reduced the circulating current. So we now had from 160 amps down to 38.4 amps. And you can see the current coming in from generator 1 and coming in from generator 2. The residual amount of current here is very likely predominantly due to single-phase, phase-to-neutral loads, because those will still want to draw the current, and the GenLink allows those currents to flow. So a substantial reduction in the overall neutral current, offloading the generators, causing them to run much cooler than with the circulating currents. The reason high neutral circulating currents appear when paralleling generators with different pitches or paralleling alternative energy sources with a 4-wire utility is that the voltage waveforms can be slightly different even when RMS voltages are perfectly matched. So that's shown here on these waveforms. You can see the blue has got a higher peak value than the red. The red has got wider shoulders, and that's the typical difference between two different pitches of generators. One might be a 2/3 pitch generator and the other a 5/6 pitch generator. The instantaneous voltages then, when these are paralleled, appear as 3 times the frequency. So here, during one cycle, we end up with 1, 2, 3 cycles here. So it appears as 180 hertz. And this voltage will drive the circulating current between the generators, the two generators. And applying the DP&L in the neutral here blocks those, introduces very high impedance, and prevents those circulating currents. So that completes our session today on real-world harmonic mitigation applications. I hope that you've found the case studies interesting and that you have a better understanding of how passive harmonic mitigation strategies can be effectively applied to eliminate the many problems associated with nonlinear loads on our power systems. I'm now pleased to address any questions that you may have.
Thank you very much, Tony. Let us open the panel and allow Tony to answer some of your questions. If you haven't done so already, we invite you to submit your questions now via the question and answer panel on the right of your screen.
Okay, I've got one question here is related to the active filter example. It says on the active filter example, you mentioned that high frequency harmonics introduced by the filter caused the premature power supply failure. Is that a typical result from the application of an active filter? And I would say yes, it is typical. It depends whether it'll cause problems with connected equipment because some equipment will be more sensitive to this very high frequency noise. But the amount of the high frequency introduced by the active filter will be dependent upon how good their input filter, or their LCL filter as it's referred to. A very good LCL filter can block those, but typically the filters are not that effective, and often with active filters or active front-end drives, which also have IGBTs, can introduce problems due to these high-frequency harmonics. And of course, high frequency is not often measured. In the case that I showed, it was just below the 50th harmonic. But they're also often above the 50th harmonic, and a lot of instrumentation doesn't measure up there. So it might look like the current distortion levels are low or the voltage distortion levels are low. But if you had an instrument that could measure all the way up to the 100th harmonic, you would see a band of harmonics at these higher frequencies. And there's a question here that under what conditions capacitor banks switching contactors are necessary in passive harmonic filters? Very good question. Many of the passive filters that are available on the market today have quite high levels of capacitive reactance, especially when they're sitting idle or at light loads. Generators systems typically can handle capacitive reactance that's 20% or less, but often these filters have 30–40% capacitive reactance. So it is often required by those competitive filters that contactors be used to switch out the capacitors at light loads. Our filters are designed intentionally to have low capacitive reactance. We guarantee less than 15% capacitive reactance. At levels that low, it's not going to introduce problems on generators. It's not going to introduce voltage boost issues on power systems. So with our filters, there's no requirement for switching out the capacitors under light loads. But I would say that with other passive filters, it is a requirement. Okay, the question here on costing, what is the comparative cost of VFDs with 18 pulse or VFDs with a passive harmonic filter? It does vary quite a bit. 18 pulse filters, now you typically use auto transformers, so they're reasonably effective. But I would say there's probably about a 20% cost reduction when using a 6-pulse drive and a passive filter compared to a multi-pulse drive system. Question, can these solutions be applied if you have grid supply as well as backup generators? Absolutely. This is a continuation essentially of the previous question. And it's even more important to treat the harmonics when you're operating off of a backup generator. In fact, a lot of times that's when harmonic problems appear. they may be fine off of the utility because of the stiffness of the utility system, and there's not that much distortion that results. But as soon as you switch to generators, the voltage distortion goes up dramatically because of the high impedance of the generator. This is often the case in hospitals where there's obviously you have to have that backup generation, and typically they're running the harmonic problems when they're running on backup, which is the last thing they want to be dealing with when they're dealing with a power failure. But when you do that, when you treat the harmonics, you have to make sure that the generators can handle the capacitive reactance at light loads. And that's why it's important to use a filter that has low capacitive reactance. But if you use a filter with low capacitive reactance, it absolutely can be applied both on utility and on backup generator. Another question, have you made studies as per IEC standards, since in Canada CSA have accepted a few IEC power quality standards from the 6100 series? Yes, we're certainly aware of IEC's 6100 series standards, and our filters, when properly applied, will allow those standards to be met. Let's see, 700 horsepower, 6-pulse VFD trip being used with 1200 kilowatts, 480 to 277 generator, 5% load, and line reactors are being used.
Gus, can you please elaborate on your question?
The question that it's causing the generators to trip could very well be, because that's a fairly heavy load on a relatively small generator. Imagine the voltage distortion would be extremely high. Certainly that could be resolved with the application of a lineator filter. Lots of questions, which is great. I don't know if we're going to be able to get through all of them. There's one, what line to generator and back switching mitigation techniques would you recommend to protect the yeah, I think there's a number of other questions. What we will do is we will review all these questions and we'll post them on the website with answers, or get answers back to all of you that have registered for the seminar. So thank you very much. I'll turn things over again to Martin.
Thank you, Tony. This is all the time we have for our webinar today. Please look for our follow-up email that will alert you to the on-demand status of today's event so that you can review any materials you've missed or simply go over it again. On behalf of Tony and the MIRS team, thank you for joining us today and taking the time to view our presentation. Have a great day, evening, or night. Thank you.
Thanks.